Hey, thank you very much, Fred, for that very general introduction. Um, Folks, can you hear me at the back?
Yes.
Thank you so much. Okay, great. Um, First of all, apologies for not being able to make it in person. I'm missing Mobisys heavily. Um, I hope I'm still able to do justice to the talk over Zoom. Um, let's get started. Okay. So the agenda for today is the following. I want to talk about challenges in the space of hearable computing. So I'll start with the broad space of hearable computing, the landscape. And then I want to talk to you about a bunch of problems, such as source separation, spatial audio and HRTF, noise cancellation, speech enhancement, bone conduction, and localization and motion tracking, and end with some thoughts. I've been working in this space for almost 4 years now, maybe more. So I'll share with you my thoughts and my opinions and what we've done. Few comments before I begin. I'll focus mostly on the problems and not on solutions. My goal is to basically shine some light on why some of the problems in hearable computing is hard, right? So I'm not going to spend too much time on the applications or what can be enabled. Rather, I'll try to kind of focus on why is this problem hard and what is it that makes it non-trivial. Okay. For source separation, there's going to be a few equations in the beginning which will be unexciting, which will be boring. I want to tell you that upfront. But I think after that, there will be no more equations, so it will be better. If the equations are not familiar to you, or you're rusty or you've forgotten, please ask. Please ask me questions anytime. I ask the organizers to have a laptop which is available for asking questions. I'll try to stop in between, so please come forward and ask questions. It will be great if we have interactions, and I'd feel happy if you learned something from this talk, something technical from this talk. Okay. With that, let me also acknowledge all my students and also Research Associate Basima. All of them are the reason why I'm able to give this talk. They've done the work, they come up with ideas and they come up with analysis. So all the good stuff, all the credit really goes to them. Okay? I just give talks. With that, let's start with this problem space. Okay, so hearable computing, at least the way we are trying to define this, is that it's sensing and computing around the human ear or head, which means that we are not only thinking about platforms like earphones, but also glasses and hearing aids, anything that's around the head, and enabling a range of applications where the applications are in different modalities. Audio, for example, has a whole bunch of applications around the earphones, around the hearables, voice assistants, noise cancellation, spatial audio, augmented reality, health sensing, and so on. Bone conduction speakers and headphones are also interesting players in the hearable computing field. We'll talk a little bit about that. So open ear audio, what are the challenges over there? And motion, many of these earphones, hearables, glasses, they have IMUs in them. And I think they also enable all kinds of applications once you're able to understand and analyze the motion. So if you stretch your imagination a little bit, my take, or my ambitious take, is that whatever happened to dumb phones from 2005 to 2015, the way they became smartphones, it is entirely possible that what we think of earphones and earbuds today could undergo a similar transformation in the next 10 years and become something that's fascinating. And I would even submit to you, this could be a first-class citizen comparable to watches and smartphones if we do the research well. Okay? So I feel that it has tremendous potential, but there are not that many low-hanging fruits. The smartphone market had a lot of low-hanging fruits in terms of everyone designs a small app and it becomes useful. in the earphone, Earable space, I think designing apps needs research, needs people like you to actually come in and design, because you cannot design trivial apps like, let's say, Angry Bird. That's not what we want. We want real capabilities that's interfacing between speech, sensors, and humans, and enabling fantastic services. Okay, so that's kind of the vision. And the natural question is, why Earables? Why now? Right? Earphones have been around for a long time. What is so special about it right now? And I want to tell you 4 arguments that I have in my head. You may not agree, or you may have other thoughts, but here is how I think about it. The first one is the following. Human-machine interaction runs over many modalities, right? So on the right side is a table where the columns are basically where humans consume bits and humans produce bits. So if you think of the visual domain of interaction between humans and machines, we consume bits in the visual domain from a screen by reading or by watching a YouTube video, right? The screen is giving us bits and our eyes are consuming it, right? But in the visual domain, we don't produce bits, right? Humans don't produce bits in the visual domain, except maybe camera, right? But most of the bits that we produce are really by typing on a keyboard or gesturing on a screen. So that's not really the visual domain. So in some sense, the visual domain is very good for consumption, but not very good for production of bits. If you think of the motion tactile domain, we do not really consume bits, right? I mean, maybe Braille is the only modality in which we consume bits by motion and tactile sensors. But in that domain, we produce a lot of bits by typing with mouses, with gestures, with screen touch, etc. Right? RF, we neither produce nor consume, right? Humans cannot produce RF frequencies. Audio, I feel, is the only frequency band in which we both produce and consume information, right? It's not a huge amount of bandwidth. It's only 20 kilohertz, but we can do both. And I think that makes audio pretty unique. And all this while, machines were unable to understand what humans produced or consumed, well, or at least what humans produced, because speech recognition, NLP, conversational AI, these areas were not mature enough. I think now with AI coming in, this modality of audio can now be unleashed, meaning human-machine interaction, a lot of it can be on audio. And I think Amazon Alexa is a good example of that, where a lot of the stuff we would do on screens is moving onto the audio domain. And I think podcasts, audiobooks are a good example of that. We would read, but now we are listening. Okay? And I think Earables is in a great vantage point to leverage this new bridge that AI has created between humans and machines through new audio bridge, this new audio modality of interaction. Okay? That's my first argument why I think Earables should be researched now. The second argument is, audio is very low bandwidth, 20 kilohertz, right? Compared to, let's say, optical, visual, which is megahertz and gigahertz, right? But one difference is optical is line of sight. There is a very narrow field of view. When you're looking at your screen, there's a very narrow field of view, and you do not know anything that's happening other than that when you're looking at a screen. And this is why a lot of accidents happen when you're crossing a road and looking at a screen, or when you're driving and looking at a screen. On the other hand, audio is actually spatial, in fact, omnidirectional, right? So you can hear audio from all sides, and your brain can extract spatial information from audio, which means audio allows humans to better connect to the situation in which they are in, thereby augmenting the physical world with audio. And I think that's a unique characteristic that Earables is in a position to bring in, that maybe visual or optics is not able to do. And I think spatial audio, HRTF, which I'll talk about a little bit, has this immersive capability or has this augmented reality feature, which is missing in other modes of interaction. Third, I think a lot of the wearable devices we know of are all in the lower part of the body. Smartwatches, phones, rings, all of these are sensing the lower half of the body, the lower part of the body. And yet there is so much data and Fitbit, and there's so much of exciting technologies that have been built around it. I think earphones is the device that's on the upper part of the body, namely the head. And I think there's a lot of information to be sensed around the head. We are talking, we are listening, we are eating, we are thinking, we are head gesturing, nodding, we are doing facial expressions. All of this information we do not have at this point because all the wearables that we have are pretty much on the lower half of the body. And I think Earables is the first device that enables an API call to the upper part of the body. Finally, I think Earables, earphones, earbuds, headphones, glasses, these are already socially accepted. If you go to a university campus, I think almost everyone is walking with a earbud on, which is very different from the Google Glass kind of a world where there was a lot of thought, a lot of risk and a lot of anxiety whether people are going to adopt Google Glasses. But I think now it's the other way. People have adopted earphones. It's upon us, it's upon you to really enable the research and the technologies and the capabilities and just upload them into the Earables and people will use it. So this is a rare opportunity where the society has adopted a product and we just need to make the services for it, as opposed to many other cases where we need to first wonder whether people are going to adopt a product or not. Okay? So these are my 4 reasons why I think Earables is the right domain and the right research landscape to look at. And with that, I want to talk about some of the problems that I want to invite you to look at if you're not already looking at it. And I think this is very interesting because there's space for a lot of people. There is depth for many PhD theses, I think, and it also overlaps with things that we know from communications and so on and mobile computing. Okay, so let's get started with source separation. It's going to be a little bit mathematical maybe, but if you don't care about that, just wait and it'll be over and we'll move on to other stuff. Okay, source separation. The high-level application is I want to wear an earphone, and as these sounds come into my earphone, come into my ears, I want to have the ability to basically graphic equalize, which means I want to amplify some sound, suppress some other sound. I want to do whatever I want with those sounds. And for that, what I really need to do is I need to separate out each of the sounds so that then I can multiply it with a large value, with an amplifying value or a suppressing value. And thereby I can do augmented reality. I can go to a city and say, I only want to hear the birds, suppress everything else. And my earphones will pick up the bird sound, suppress everything else, and only play that. Right? Or it could be someone else talking to me in a restaurant. I only want to hear that person and suppress everyone else talking. Okay? So this is called the source separation problem. And the general problem statement is as follows. I have M number of microphones. For the sake of our simplicity, let's say 2 microphones. Let's say multiple K sources are coming to this microphone. Let's say 2 sources. And what I receive is X1 and X2. X1 is the signal that I receive at microphone 1, and X2 is the signal that I receive at microphone 2, that is X1, X2. The source separation algorithm asks this question. If X1 and X2 is the input to the algorithm, your output should be the source signals S1 and S2. That's what you need to do. Okay. This is basically the input-output definition of the problem. Now, if you model this with very simple math, it turns out this is basically a matrix, which is often called a mixing matrix. And for now, you can just give random values to this matrix. So X1 is nothing but A1 times S1 plus B1 times S2. X2 is nothing but A2 times S1 and B2 times S2. Okay? That's what you're getting. And your goal is somehow to figure out A, this matrix, and B, this source vector S1 and S2. Okay? That's the source separation problem. Now, observe that it's very tempting to think, oh, this is an easy problem. Why? Oh, because there are two-dimensional, two variables, two unknowns, right? Note that that's not the case because this matrix is also an unknown. You do not know how the signals got mixed, right? So actually, in this case, there are 6 unknowns and 2 knowns, 2 measurements, which means it's heavily underdetermined. Okay, great. So here is a visualization of the source of the measured signals X1 and X2. The x-axis is X1, the y-axis is X2, and each of the dots are each of the values of X1 and X2 that you get from your microphone. Okay? And these are 3 different instances. You know, if I tell you, can you tell me in this first case, what are the 2 sources? You might be able to say, you know what? This, by the way, guys, can you see my cursor? Yes. Yes, thank you. So it might be tempting to say, you know, this is the one source and this is the other source. And actually, you will be right. This is actually one source and this is the other source, because there is some uncorrelation between the sources, and therefore you might be able to separate it out. But that's actually a very slippery slope, because that temptation can lead you to a wrong inference. For example, if I tell you this one, and if I ask you what are the 2 sources, S1 and S2, a lot of people I ask, they say, this is one source and this is the other source. That's completely wrong. Okay. Actually, it turns out the first source S1 is a signal that has some component over here and some component over here. And the second source is a signal that also has some component over here and some component over here. And they have mixed in a way as if there are 2 clusters, but actually S1 is everything on the bottom of the diagonal line, and S2 is everything on the top of the diagonal line. This is another case of mixing where S1 and S2 is completely mixed, and you cannot say anything of which dots are S1 and which dots are S2. But the source separation problem is essentially asking the question, given these black dots, can you say which dots are red, which dots are blue? Because the red dots come from S1 and the blue dots come from S2. That's the problem definition. Okay, good. So I hope you are with me thus far, right? So the general source separation problem actually occurs in vision as well. Maybe, you know, you take a picture of a window, a glass window, and whatever is behind the glass window, your picture gets that, but also there is some reflection on the glass window. Your picture gets both. And what the picture actually has 2 different images mixed. And source separation is helpful over there, where the mixing matrix is very unknown. But in many of our applications, such as RF, audio, and so forth, this mixing matrix is actually a steering matrix, right? It's the angle of arrival matrix. And that is the matrix we have played with in many, many occasions, right? And that is where things become a little bit simpler, because now we don't have 4 unknowns. We only have 2 unknowns, which is the AOA, the angle of arrival of the 2 signals, and of course, 2 more unknowns, which is S1 and S2. So now what can we do? One thing we can immediately do is, if we know the AOA, then we can immediately solve it because we know the matrix A, 2 equations, 2 unknowns, we can immediately solve. It's a determined system. I hope you all agree with that. Even if there is noise, you can do least square and you can solve it. Not a problem. But now let's say you do not know A, the matrix A, which means you do not know the AOAs. And there can be many reasons why that happens. But suppose you know that you know the distribution of the sources S1 and S2. So I tell you that source S1 is a Gaussian distribution with this mean and variance. Source S2 is another Gaussian distribution with a different mean and variance. Now I ask you to estimate S1 and S2 from X1 and X2. Then what can you do? Well, then you can do something where you can essentially do a maximum likelihood estimation, which is essentially saying the following, which is saying, I don't know A, but if I pretend I know A, then I can solve for S1 and S2, right? If I pretend that I know A, I pick some random value of A, then I can solve for S1 and S2. And then I can ask this S1 and S2 that I solved for, do they obey the distributions that are given to me, the 2 Gaussians that are given to me? Now, for every value of A, for every possible value of the matrix A, I can solve for S1 and S2 and see which matrix A gives me an S1 and S2 that maximizes the likelihood of those observations. Okay. So if I know the distribution of S1 and S2, I can solve quite well. It actually works quite well, even if I do not know A. Okay. And this is basically maximum likelihood combined with gradient descent. Great. Let's make the problem harder. You do not know A, you do not know S. Okay. Then what can you do? And this is where a very, very popular algorithm is called the independent component analysis. Those of you working in audio speech, audio signal processing, I strongly, strongly encourage you to look at this if you do not know this already. Independent component analysis says that if the two sources here are independent, not correlated, independent, and what's the difference? Correlation means that in expectation, the expectation of S1 and S2, the joint expectation is expectation of S1 times expectation of S2. That's correlation where the expectation you can separate them, multiply them separately. Independent says, oh, the distribution is independent, meaning P of probability of S1, S2 is equal to the probability of S1 times the probability of S2. So each individual samples, they are independent, right? In that situation, ICA actually is able to separate, okay, the two sources, even if you do not know A. Okay? The intuition actually is quite simple once you see it. It's not at all difficult. And maybe I'll quickly tell you this. If you're not familiar, it's totally okay. But I want you to even pick up the keywords, for example, SVD, because I think it's a good one. If you want to spend time on something in audio signal processing, this is the one to spend time on. Okay. So here is the 4 steps of independent component analysis. And I promise 2 slides later, we are not going to have math anymore. Okay. Okay. So step 1 is you take X, which is your measured vector, and you model the covariance of X, which is X times X transpose, the expectation of that. What is X, which is AS? This is your A matrix and your S vector. So AS times AS transpose, you do all of that. And then A, you do a singular value decomposition, which is U sigma V transpose. S transpose is independent. So SS transpose becomes a diagonal matrix, which means almost an identity with a scalar. So you get basically U sigma square U transpose. In other words, SVD says that any matrix A can be separated into multiplication of three matrices, U, sigma, and V, sigma being the singular values. And the covariance of X is a function of U and sigma, and V disappears. This is the model. Now, suppose you take the second step, you take the measurement of X and you compute the covariance. The first step you modeled, second step you actually compute the covariance. You will get some eigen decomposition. You'll get singular value decomposition, which is E, D, E transpose. And now, because these two are the same, you know that E is U and you know that D is sigma square. In other words, long story short, by looking at covariance, you have found out two of the matrices of A, two of the SVD matrices of A, which is U and sigma. The only thing that you do not know is V, right? Because A is U sigma V. By looking at the covariance, you know U and sigma, you only don't know V. Okay? This is actually beautiful because without knowing anything about A, you figure out two things about A just from looking at the covariance. Third step, now look, S is basically A inverse X from this equation, right? And A inverse can be written as U sigma V transpose inverse. So the only thing you do not know over here is V. So you can write the source signal, the estimate of the source signal, as a function of V, which is the only unknown, right? And now what you can do is you can say, for different V's, my source signal should be independent. So let me search over all possible V's such that the right V maximizes the independent between S1 and S2, where S1 and S2 I have modeled doing this. So when you have two distributions, the way to separate them, one way to do it is scale divergence. There are many ways to do it. So you basically find the right V, which will maximize the difference between two distributions, where one distribution is your estimate of S1, the other distribution is your estimate of S2. And once you maximize that, whichever V maximizes that, that's your V. And once you have V, you have everything, because you have U, you have sigma, you have V, and from these three, you have A, which is your steering matrix. And once you have A, you have S, because you can solve it. Okay? It's a little bit involved, but this foundation can help you in many, many signal processing tasks, because understanding this means you understand many of the things around source separation and signal separation and denoising, speech enhancement, etc., etc. Okay? There are many other algorithms: independent vector analysis, matrix factorization, matrix completion, sparsity, compressive sensing, and so on. All of this has happened in speech separation, in source separation, okay? When A and S are unknown. Great. Now, another way to simplify, because many of the applications are not random signals, another way to simplify this source separation problem is by assuming that the source is a speech signal. And if it is a speech signal, then there is very interesting properties of speech. One of them that has been shown empirically is what is called TF disjointness or W disjointness, which says that when two people speak, if you take their speeches STFT, let's say the one is the red, one speech comes from, one speech produces all the red boxes and the other speech produces all the blue boxes. Okay. If you look at the red and the blue boxes, there's a very low probability of the red and the blue boxes overlapping in time frequency bins. This has been shown. Okay. So if you have that, and then now you are recording speech on your earphone microphones, means you have two STFTs from two microphones. And now what you can do is you can calculate the phase differences from each, right? For each TF bin, you take this red bin, you take this red bin, you calculate the phase difference. That you can do, divide. And from those phase differences, you can get the time difference. And what you should see is that all the red speeches give you one delta T, and all the blue speeches give you another delta T, because they come from different angles of arrivals. Therefore, their delta T's are different if they are speech. If that happens, then from these red and blue distributions, you can pull out their AOAs. And once you know the AOA, you know the A matrix, you can solve for S. Which means this is an indirect way of figuring out the A matrix. You could have beamformed. That also is something you can do. You can beamform and get the A matrix, but that beamforming quality is worse because it does not utilize the information that speech signals are disjoint in the time frequency domain. If you utilize that information, you're going to get a much better AOA, and from that, you can separate the sources. Okay. Finally, all of this is good when the number of sources are the same as the number of microphones. When the number of sources increase, that becomes much harder, because now it's underdetermined, right? There are many more sources. And because there are many more speech sources, you're no longer going to have the red and the blue and the green in different time frequency bins. They're going to start overlapping. The red and the blue and the green are all going to be in the same TF bin. Then your histogram is going to be very, very noisy, and you won't be able to separate the AOAs. As a result, that is where neural networks are coming in, and neural networks are saying, for underdetermined, it's hard to model, hard to do anything classical. Let's see what neural networks can do for speech separation. And the results have been quite interesting. For example, TASNet is a popular one that gives you speed, that does source separation even in underdetermined settings, which means two microphones, maybe 3 or 4 sources can be separated. Okay. Here is a citation to a very good summary of the landscape of source separation today, but it's still a very active area of research. And if you're interested in this problem, here are some of the challenges that are still open. One, number of sources are unknown. Many algorithms assume that you know the number of sources, such as, oh, there are 4 sources with 2 microphones. But if you do not know how many sources, then it becomes a pain. 2, reverberations, which means multipath, makes this problem much harder. Okay. 3, in low SNR regimes, when there's a lot of diffused background sound and all kinds of non-stationary sound, it's a problem. Real time is a problem. Tiny models is a problem. If you want this to run on earphones, that's a problem. Lot of work remaining. We have done some work in this space, in source separation. I'm just pointing this to you. I don't want to talk about what we've done, but if you're interested, feel free to look at some of this. Great. Any questions thus far? Okay, it was dry. I know it was post-lunch, so maybe I put you to sleep even more. But from now on, there's no more equations for sure. Hopefully, this would be a little bit more exciting. But I wanted to get done with the math first, and I also wanted to give you a little bit of sense of what the signal processing community is doing, which I am learning myself. There's a lot of things to rabbit hole into. Okay, spatial audio and personalized HRT. Okay, so in this problem space, the question is the following. Suppose I play a voice from your earphone which says, hello, please come this way. Today, if I ask you, was that sound from your earphone or was it someone else calling you? Do you think you can say whether it's from the earphone or not? I think you can easily say that. You can easily differentiate when someone actually calls you versus whether when the sound is being played from your earphone. Okay, you can easily tell the difference. So the question we have, or the problem people have proposed is, can you play the sound in your earphone in a way such that the brain gets fooled into thinking that it's a real sound, that someone actually called me? What does it take to do that? Okay. And the answer to that question is what is known as a head-related transfer function. Essentially, what you need to do is the following. You need to take the sound and then you need to filter the sound, and you play the filtered sound through the earphones such that it sounds absolutely real. And this filter is called the head-related transfer function. Okay, let's look at what does head-related transfer function. Okay, so this I'll quickly soon tell you what head-related transfer function means, but let me just say that this research actually began in the 1960s, where people were trying to understand how sound hits your face and how it actually travels around your head. There's been a lot of work on this, but it's still a very, very challenging problem. Why is it challenging? Okay, it's challenging. The first reason is when a sound hits your head, it actually diffracts, means it actually curves around the cheeks and around your jaws. Moreover, it actually bounces in your pinna, in your ear. It bounces in different ways. And after all those distortions, it enters your ear canal. In fact, human face and human ears have evolved over time so that they can actually guide the sound intelligently, so that your brain can actually understand spatial properties of the sound, such as which direction is the sound coming from, how far is the sound, how big is the room, and so on. All of this distortion that your head and ear creates is called the head-related transfer function. And it's a function of theta, which angle the sound comes from, and a function of frequency. Every frequency has a different filter, has a different HRTF. So the question is, if you can learn what the HRTF is, then you can fool the brain. You can basically take any sound, any voice, let's say, please come here. You take that sound, which is XT, and you basically filter that with the HRTF, basically multiply XF with your HRTF. Which HRTF do you take? Oh, if you want the sound, if you want the voice to come from northeast, you take that theta, you take the corresponding HRTF and you convolve with that. And then you take an IFFT and you play that sound through your earphones. Your brain will think the sound is coming from northeast because the HRTF you've used is the northeast direction HRTF. Okay? If you do that, you're done. That can enable a lot of applications. For example, if you are in a shopping mall and you tell your earphones, hey Siri or hey Alexa, take me to Starbucks, then your Alexa would say, follow me. But the follow me sound would appear to your brain as if it's coming from some direction and you're just going to follow that direction. It's as if someone is escorting you with a voice prompt towards Starbucks. Right? This is kind of spatial audio, spatial augmented reality navigation. You can obviously do VR gaming, right? Or you can be in a virtual orchestra where the guitar is coming from your right, the piano is coming from the front, the drums is coming from the left. You can be in virtual Zoom meetings where people seated on a table, their sounds, their voices comes from different directions. So all of that is possible, but the challenge is HRTF. So why is it hard to get HRTF? What do they do today? So today HRTF is actually a solved problem if you measure HRTF in the lab in the following way. This is what people do. They take you to an anechoic chamber where there's no reverberations, no echoes, or very little reverberations. They make you sit in a table and they make your head rigid, immovable, by clamping your head on a chair, on the back seat of the chair. And then they have speakers that move around you and they play sounds from different angles and different locations. And they measure what your ear hears from some in-ear microphones. And whatever those microphones record is actually the HRTF for the theta in which the speaker is located. So for every angle and every location, you measure the signal, then you deconvolve with the source signal, and that gives you the channel, and that channel is your HRTF. Remember, the room does not have reverberations, so there is no room impulse response. This is accurate, but you cannot do this at home, right? You cannot have this kind of a setting at home. So the question is, what can you do at home? Because everyone has a very different HRTF, and you want to measure your HRTF if you want to fool your own brain, right? If you want to wear earphones and do this voice-based navigation, you need to know your personalized HRTF. That's very difficult because you cannot do that measurement inside your house. So what are people proposing? Okay, so today what earphones have is a generic HRTF, meaning Apple would measure the HRTF of a bunch of people and use their average and put that in AirPods. I mean, every other earphone company would do that if they have HRTFs. And that HRTF will be used when you use AirPods or earphones, right? But that is someone else's HRTF on you. It's reasonable, but not exactly personalized to yours. And that is why you can easily tell that this is your earphone and not actually a real sound. Okay? And actually, it turns out this is not optimal. We did some experiments with a generic HRTF. The errors are actually more than 20 degrees, 30 degrees. Other people are trying something interesting. They're shining a laser, like from your smartphone or from some gadget, on your own face. And from that, it's trying to reconstruct the terrain of your face. And from that, do sound field reconstruction, basically ray tracing in audio frequencies. And from that, they're trying to estimate HRTF. The skin and the hair and all those properties, those things don't get captured from a visual scan. That's why it's also not accurate. Okay. Finally, and this is an interesting part, even if you get the precise HRTF, your personal HRTF, it's still hard to fool your brain. Why? Because your brain also takes into account the room impulse response, the reverberations of the room. So if you play the HRTF only, and your eyes see that you are in a big room, your brain will think, hey, how come I'm in a big room, but what I'm hearing doesn't have a lot of reverberations. And whenever your brain says, I expect a lot of reverberations because I'm seeing that this is a big room, but what I'm hearing doesn't match that, your brain immediately thinks, this is actually fake sound. This is not real sound. It must be coming from the earphone. So if you want to really if you really want to fool the brain, you need to also add the room impulse response into the HRTF or along with the HRTF. That's when your brain will be fooled. And that is what is called externalization. That's the technical term. That's when you achieve externalization. And externalization is very difficult because as you're walking in a shopping mall, how would you know what exactly is the room impulse response at the location in which you're standing? So here is the challenge for you. Develop techniques, algorithms to accurately measure the personalized HRTF at home And the second challenge is also learn the room impulse response of the room from the user's location on the fly. In other words, can you do something like this? You will speak, your earphones will record, but whatever you've spoken will reverberate in the room and come back to your earphones. Can you subtract your own signals, which came directly? Can you subtract that and thereby pull out the room impulse response on the fly? That's the challenge. Okay. And I think it's not easy to do that. Questions, guys?
If you have any questions, feel free to
yes.
come to the front.
Actually, there's a lot of reverberation in the room. So if you could come close by, that will be great.
Hi, Romit, can you hear me?
Yes, I can. Yes.
Yeah, I'm Nakul from UMD College Park.
Hi.
Great talk, very inspiring, really motivates to work on HRTF.
Hey, I'm not done yet, by the way. Yeah, I'm kidding.
So just a quick question on the last point that you mentioned, that if we want to get the room impulse response from the person who's speaking, that will be the room impulse response from the speaker and the listener's location at the same place, right?
Exactly.
So is that like different from what we would like to have, for example, drum sets playing at some other location?
Spot on. Even if you get the room impulse response, it's from your transmitter to your receiver, right? That's not the room impulse response of what you want from someone who's calling you from somewhere else, right? But what I'm saying is, at least if you have some sense of the room impulse response, it'll help your brain. Maybe there's a greater chance of fooling your brain compared to not adding the room impulse response.
I see. Got it. Thank you.
Yeah. Okay. I'm running very late, so I'll skip something and I'll switch to a different another. I was going to talk about open ear noise cancellation, but I'll skip that. The high level idea question, the high level challenge was all noise cancellation earphones today block your ear. Can you design noise cancellation without blocking your ear canal? And I'll point you to some papers. There are some papers over here that talk about that. I think that's a very, very hard challenge. And because it's super hard, I'll skip it because I think that's almost impossible. Okay. Next challenge is speech enhancement at low SNR. Okay. You know, speech denoising is an important problem. It's a growing problem because as we are moving around, there's a lot of ambient sound. And if you're going to take phone calls and talk to your voice assistants on your earphones, decoding speech, denoising speech is very hard. A lot of people are working on speech denoising, right? I think Nirupam's group you guys had a paper earlier in the session today talking about speech denoising. I think Sham had a paper on clearbuds on denoising. We have papers on denoising. There's a lot of work in neural network, non-neural networks that's happening in denoising, all in the audio domain. One opportunity I want to share with you is that the IMU in your earphone also actually measures vibrations that comes through your bones, through your face. But this is a very low bandwidth, only 400 hertz vibration. But the good thing is the IMU vibration, the IMU senses your speech, but not any of the ambient interferences. So if you think about it, your microphone is sensing your speech, but also a lot of ambient sounds, interference. Your IMU is sensing your speech at a very low bandwidth, but no ambient interference. So the question is, can you recover speech from the IMU signal? Because if you can do that, that will be great because that signal, that recovered signal, has no interference whatsoever. It's the pure speech signal. So this becomes a question of super resolution, right? A lot of people are able to do super resolution on images where they take a very low resolution image and do super resolution and get a high resolution one. With IMU, the challenge is I give you a very low resolution IMU signal can you convert to a very high resolution audio signal? Of course, it's in a different modality. One is IMU, one is audio, but they both are vibrations, and maybe that is possible. We tried it, we could not do it. Let me say that up front, but maybe you can do something better. Of course, deep learning. And the point I want to make is, this is not some random low resolution signal. This is basically an aliased version of the speech signal. So the structure of distortion, which is aliasing, right? Your 500 hertz signal is actually a heavily aliased version of your 8 kilohertz speech signal or 16 kilohertz speech signal. So it's not some random interference or some random distortions. Because it's aliasing, my feeling is super resolution should work. We have not been able to do it yet. We have done something over here, but I'm not going to spend time on that. Instead, I'm going to just leave it to you as the challenge is, how much speech can be recovered from the IMU alone? That's the first question. And the second question is, how much improvement can you get in speech denoising if you combine the IMU and the microphone together? Right? Together, you should be able to do better than what the microphone is doing, or even what any other neural network techniques are doing, because now you have additional information that is devoid of any interference, right? So maybe this is also a joint neural network problem where you combine microphone and IMU, and we have done something over here, but I think there's a lot more room for improvement. Question? Okay. Last quick, these two are quick ones, but I also wanted to talk to you about maybe just this one, bone conduction one, because this I feel is something that's not in the general class of problems that get talked about. Okay, here is the problem. These earphones that we are wearing, it's very difficult to wear it all the time. Okay, we want earphones to be open ear, right? It's not going to block our ear. It's more comfortable. It's also good for health because these earphones block air circulation, and blocking air circulation means bacteria can develop in your inner ear. If you design earable devices which are open ear, in fact, I think Sony has something called Donut, which has a hole in the earphone, then air circulation can happen. But that's a problem because the sound quality and all of that goes down. So one area is, why not use bone conduction? Which means I will basically vibrate signals. I'll vibrate your skull, and your inner ear can actually pick up that signal. But it turns out that bone conduction speakers, the quality of the sound degrades or is not very good for many, many people. Many people do not like that. Okay. So that is kind of surprising. Why? Because, all we need to do is that we need to understand the bone channel. If you know the channel from your skull all the way to your inner ear, to your cochlea, if you know the channel, let's say the channel is HB, B for bone, right? So what your cochlea is receiving is Y equals X convolved with HB. X is the source signal. So if you knew HB, then what you should do is the following. You should pre-code the signal with X convolved with HB inverse. And then when this signal gets transmitted, HB inverse will get cancelled with HB, and what your inner ear, your cochlea will hear will be just X. And that will be clear source signal, right? So the real challenge is, can I get HB? Can I learn HB? Okay. Why can't you learn HB? Well, the reason you cannot learn HB is because you do not have a microphone inside your cochlea, which is going to give you the received signal Y. Right? That's the reason you cannot learn HB. So then what can you do? Right? So the question I'm posing to you is, can you learn the bone channel without implanting a microphone inside your brain, inside your cochlea? One approach is feedback based. What is the idea? I am going to guess some HB, some channel, bone channel HB. And remember, bone channel HB is basically a vector, right? It's a vector. It's a bunch of filter taps. So I'm going to guess some random vector, HB. I'm going to guess the inverse of that, HB inverse. And I'm going to take that vector, HB inverse, convolve it with X and play it. And I'm going to ask the user, how good was the sound? The user would say, it was bad. I would say, oh, that means that HB that I have guessed must be really bad. Let me change HB into something else. I change HB, and again, I do the same thing, and I say, how good is the sound now? And the user says, it's a little bit better. And then I say, oh, that means the direction in which I made the change from the first HB to the second HB, that must be the right direction. And I change more in that direction. Basically, I do gradient descent, right? So I can keep changing HB such that I go towards a direction in which the user's feedback gets better and better, right? So this is like gradient descent, where you do not know the function on which you're gradient descending. You do not know fx, but you're asking what is fx by every time by asking the user. Now, here is the big problem. Okay? The big problem is the user has a very coarse-grained perception of sound. Meaning, if you change HB multiple times and you ask the user, how is the sound now? Is it better or is it worse? The user would say, it's pretty much the same. I don't know if it's better or worse. Which means what? Which means the gradient of the function is flat. It's like a staircase function. The user's perception function on which you're trying to do gradient descent is actually a staircase function like this. And gradient descent algorithms will not work on any staircase function. Why? Oh, because all gradient descent algorithms assume that once your gradient is zero, meaning that it is flat, you've come to the minima. But with a staircase function, you're going to come to the flat part many, many times, and it's not going to work at all. So all gradient descent based channel estimation is going to completely fail. Okay. So here is the challenge for you. Okay. The challenge is, first is minimize an unknown staircase function. Very general problem. You have a staircase function. Can you do gradient descent on this? What is the best way to do it? Okay. Observe that this has nothing to do with Earable computing. It's a very general question. Second question is, can you do this under a constraint of the number of iterations? Because you don't want to ask the user 100 times, hey, how is it? Hey, how is it? And so on, right? You want to ask the user maybe 10 times. So you want to do gradient descent on the staircase function within 10 times. How can you do it? That's an even harder question, but we are struggling with this question because we are trying to see how can you optimize a function which has so many flat components. And of course, it's not convex because once you have a staircase-like function, it does not remain convex anymore. Okay, guys, I think we are out of time. And the last problem I was going to talk about is localization, where there's a lot of advantages we get in motion tracking from IMUs on the earphone. And I can point you to, again, papers that talk about some of this. These are some of the papers we have worked on in this space. I didn't want to talk about any of our work, but if you want, you can get our paper from our website on Earable computing. With that, once again, thanks to everyone for listening at so late in the conference. And I also, again, want to thank the organizers for inviting me. I'm very happy to take questions. Thank you, guys.
So we're a bit short on time, so we can probably take maybe 2 questions.
Sorry, Sorry, can't hear you at all.
Oh, I'm sorry. I was saying that we're slightly behind on time, but we can take a couple of questions. So if you have questions, please step up. And you probably have to stand here to speak.
Hi, thank you for the nice talk. I'm Jinping from Columbia University. I have a question on the earbone conduction part. So I'm just like curious, do you think it is like possible to also for the earbone, this kind of headphones, to do kind of noise cancellation like the over the ear earphones?
Right.
Do you think that's a possible direction?
That's right. That if you solve the bone channel estimation problem, you can do many other things, right? And I think noise cancellation is one of them, but I still think noise cancellation is very hard because you have to do adaptive filtering and inverse channel estimation. The easier application, if you can estimate the bone channel, is better quality sound from bone channel speakers. But yes, it would be a step towards open ear noise cancellation. You are absolutely right.
And so a follow-up question to this is, I know that for a sort of like aging problem, like will cause some hearing loss. So if like the aging people doesn't have conductive hearing loss, probably like the earbone like conduction hearing assistance might be a good choice. But recently, like a lot of hearing aids are like designed to tend to be like all in the ear style. So I'm just like curious, what do you think about this kind of hearing aids design for like the current world? Like whether it's good to incorporate some of the earbone conduction part, or yeah, just your opinion on this.
Right. So one difference between hearing aids and bone conduction devices is that hearing aids have an advantage where they can put the microphone all the way into the ear canal, right? And they have microphones over there which act as reference microphones, which is very valuable because it can estimate what the eardrum is sensing. With bone conduction, you cannot do that. You do not have a earphone or microphone inside the ear. So bone conduction is more suited for speakers, right? As opposed to microphone-based applications.
Thank you.
So we have time for one more question. So please step.
Hi, Romit. Thank you for the great talk and tutorial. I got to learn a lot of new things today.
Thank you. Thank you very much.
I had a question regarding you wrote bone conduction and glass speakers. Could you explain more about what glass speakers are?
Glass speakers is basically, yeah. Go ahead. Sorry, finish your question.
So that was the question. Like I didn't get and I hadn't heard about what they are. So I just wanted to ask.
Right. So glass speakers, what I wanted to say is many of these frames like Amazon frames and Bose frames, right? They have speakers on the stick part, right? And that sound quality is also not great. Why? Because the sound that comes from speakers over here, that sound basically diffracts, reflects, and all of that, right? So there is a channel from that speaker all the way into your ear canal. I want to learn that channel as well. Because again, if I can learn that channel, I can invert that channel, right? So that the sound quality is great, right? In fact, I might also want to learn that channel to minimize leakage, meaning I want the sound to be audible to my ear, but not audible to anyone sitting next to me, right? For all those reasons, I also want to learn the channel or estimate the channel from the speaker to my inner ear, to my eardrum. And that also has this problem of human feedback-based channel estimation.
Got it. Thank you so much for explaining.
Thanks very much. Yeah.
Alrighty. So Romit, thank you so much for the fantastic keynote. I just want to also thank you for not only giving us so many sort of valuable information on acoustics, but also providing these open challenges, right? These are things that hopefully can energize the entire community to work on these exciting problems. So with that, please join me in thanking our keynote speaker.
Thank you so much, everyone.